This is Matt, 2021, question 1J.
It are the A, B, C, and D are distinct real numbers chosen to define 4 points. A, which is A, B, big B, which is B, C, big C, which is C, D, and big D, which is D, A. I want to determine necessary and sufficient condition on A, B, C, and D for the quadrilateral A, B, C, D to have equal side lengths. So maybe let's try and work out what the side lengths are. Well, because we know the coordinates, we can work out their length by using Pythagoras. So for A, the length between A and B, we're going to have the difference, the length is squared, it's going to be B minus A all squared plus C minus B all squared. And then we can do the same thing for the other three side lengths, which gives us that length of BC all squared is C minus B all squared plus D minus C all squared. And similarly for CD squared and DA squared. Note that we don't have AC all squared and BD all squared, because when we define a quadrilateral we go clockwise, so A is joined to B, which is joined to C, which is joined to D, so there's no line joining A to C. Okay, so what do we know? So you want these lengths to be the same. Well, this is the length squared, but why is this the same thing? Well, because our lengths are all positive, the side lengths are equal if and only if the side lengths all squared are equal. So we can just compare these expressions. So if they're equal, we need B minus A all squared plus C minus B all squared is equal to this, which is equal to this, which is equal to this. So let's examine what conditions we need, maybe working left to right. So for this equality to hold, we see that these two cancel out. So we need B minus A all squared is equal to D minus C all squared. And now looking at this one, we see that this term and this term cancel out. So we need C minus B all squared is equal to A minus D all squared. Now looking at these two terms, we see that these two cancel, which means we need D minus C all squared is equal to B minus A all squared. It's already covered here. Now looking at the other combinations, we are these two. Well, we see that B minus A all squared is equal to D minus C all squared, so these cancel out. And the same thing here. And we, in fact, by checking the permutations, we see that these are the only two conditions we need for these equalities to all hold. And in fact, it's an if and only if. So what can we do with these two equations? Well, maybe the answers give us only maybe only one of these conditions. So it's either if and only if A minus B all squared is equal to C minus C all squared. So we only have one of them. So maybe we want to try and simplify these down. Well, we can try and write this on both these equations on one side of the equal sign by maybe writing this as a difference of two squares. So you can write this first equation as B minus A plus D minus C times by B minus A minus D plus C equals 0. And we do the same thing on the other side. Okay, so for this equal is 0, either this is equal to 0 or this is equal to 0, or both. But why can't it be both of these being 0? Well, suppose both of these brackets are equal to 0, then B minus A is equal to D minus C, but also equal to minus D minus C, which must mean that B minus A is equal to 0, which means A is equal to B. And that's a contradiction because we are told that A and B are all distinct. And we can do the same thing for the other side, which means that only for each of these two equations, only one of these brackets can be 0 at the same time. But what else do we notice about these? Well, we see that this bracket and this bracket are actually the same thing. This is, in fact, this bracket times by minus 1. So for this, these two equations to both hold, either this one is equal to 0, and so this one is also equal to 0, and these two are not equal to 0, or if this one is not equal to 0, we need this bracket to be 0 and this bracket to be 0. So you have two cases. So either this one is equal to 0 by itself, or both this and this are equal to 0. And I'll call these equation 1 and 2. So maybe let's try and examine these two equations, because we've got two simultaneous equations. So let's try and solve them. Well, if you see that equation 1 minus equation 2, in fact, eliminates B and D, and we're left with 2C minus 2A equals equal to 0. And simplifying this gives us that C is equal to A. And why is that a problem? By the same reasoning, as A, B, C, and D are distinct, this can't occur. So this possibility can never occur. So the side lengths are equal if and only if B minus A plus D minus C is equal to 0. And therefore, rearranging this gives us exactly A minus B plus C minus D is equal to 0. So our answer is D.